things now. 2 things. Oh, is it started? Okay, we're gonna learn about 2 things here. Work and energy. Are you ready?
Yes.
Okay, great. So I get a job, and I say, hey boss, I'm here to do my job. And the boss says, well, Shana, when you get the job here, you're gonna have to work. You've got to do a lot of work. And I say, well, that's okay, I like to work. He says, okay, Shana, here's what I want you to do. You see that wall? Yes. Press against that wall. And I go like that. No, harder. Like that. Harder. Like, okay, I'm pressing as hard as I can. He says, okay, Shana, and when I come back in 15 minutes, you better have done some work. So I say, okay, so for 15 minutes, I'm pressing really hard. See how white my knuckles are? I'm pressing so hard. Look at all that force I'm exerting. Then the boss comes back in 15 minutes. He goes, Shana, what have you been doing for the last 15 minutes? I said, well, I've been doing what you want me to do. I'm pressing against the wall. He says, no, Shana, you may have been pressing against the wall, but you haven't done any work. Tell me, what would I have had to do to convince him that I did work? That there's some evidence that I actually accomplished anything? What would I have to do? What's that again? Yeah, break the wall? Okay, great, break the wall. Any other ideas? What would I have to do to this wall to satisfy that my boss that I actually accomplished something?
Show him your very fake handprint.
No, it's not. I mean, I could do that in 1 second by just pressing. Okay? Tell me more. What would I have to do to the wall?
Move it.
Is anyone? Yeah, thank you. Move it. Anyone thinking just move the thing? If I move the wall, then he comes back with some evidence that I did something, right? Because just to exert a force and not change anything is worthless. It's like trying. When someone says, well, I tried to be on time, but I was late. Well, trying to be on time is irrelevant, right? It doesn't do anything. Either you're late or you're not late. There's no try. And that's the same thing with this idea of work. Exerting a force is not enough. There has to be some evidence that you accomplished something, that you changed something with that force. And so that brings us to the concept of work, where we bring together 2 apparently disparate concepts. And those concepts are force and distance. And here it comes, work equals force times distance. Not only did you exert a force, but something moved a certain distance. And then you can say, okay, I did work. I accomplished something. Here, let me give you a quick example of this. Here's me, and here's some huge crate, okay? And I exert 100 newtons of force on this crate, and I move the crate 5 meters, okay? So I exert 100 newtons of force on the crate, and I move it 5 meters. So the crate started there, and the crate kind of ended there, okay? I'd like everyone right now using this formula, please tell me how much work this guy did. Is everyone getting 500? Yay. But tell me, what's the units? Are you guys getting work is 100 newtons times 5 meters? Are you guys getting 500 Newton meters? Good, because that's it. That's what work is. Work has the units of Newton meters. Except for one thing, in the same way that we let kilogram meters per second squared be the same as newtons to honor Isaac Newton, we want to honor another guy named James Joule, who did a lot of important work with work and energy and heat. Okay, and so we don't call it Newton meters, no siree, we call it joules, named after this guy named James Joule. And his name is actually spelled Joule, James Joule, not like Jewel, which is like a precious gem or something. 500 joules or 500 J. So you guys okay with that? Work, force times distance, pretty easy.
500 Justins.
Let me give you another scenario. Imagine a choo-choo train that's going across the front of the room. In fact, you can see these blue lines on the floor. Imagine those are the railroad ties. So the train is going across the room, and I'm standing at the side of the train, and I exert 100 newtons of force this way. I'm pressing as much force as I can, 100 newtons of force this way. The train goes 5 meters that way. How much work did I just do on the train? Did I do 500 joules of work? Me exerting 500 or rather 100 joules that way, and the train going 5 meters that way?
No,
Why not?
because it didn't move that way.
Thank you. Imani says because the train didn't move that way. The train moved that way. Do I get to take any credit for the train's motion in that direction? No way, not if I'm exerting force that way. You see what I mean? Where would I have to be in order to say, hey, I did 500 joules of work on the train? Yeah, I'd have to be over here, right? Pushing the train this way. If I exerted 100 newtons of force on the train and moved the train 5 meters, even if I wasn't entirely responsible for the train's motion, I could have almost no influence on the train's motion, but I would have a little bit of influence. I would have done 500 joules of work on the train if I moved the train that way. You see? So it's not just force times distance. It's actually the force that's in the direction of the displacement times the distance. You see? Or the force in the direction of the motion or the velocity. So I've got to give you a new formula. Work isn't just force times distance. It's the force in the direction of the displacement times the distance. Or we could think of it in another way, and I'm going to show you both ways to think about it shortly. We can also just say, hey, work is force times the distance in the direction of the force. Either way, you're only exerting as much work as you can take credit for. You get credit for the thing moving in that direction, then the work you did is the force you exerted in that direction. You're exerting a force in that direction, then the only work you get credit for is whatever distance the thing goes in that direction. Here, let me give you a kind of an easy problem about this. Here, I've got a suitcase. And the suitcase has this little strap, and I'm gonna walk this way, pulling the strap. I'm going to exert 100 newtons of force at a 30-degree at a 30-degree angle, and I'll walk 10 meters horizontally. If I'm exerting 100 newtons of force and I walk 10 meters, does that mean I just did 1,000 joules of work? Everyone's shaking their head. So someone tell me, how would I figure out, or tell me, why is it not 1,000 joules of work?
You're doing all the work.
What's that?
You're not doing all the work.
Okay, tell me more. What do you notice about the direction of the force and the direction of motion? Yeah, Noel?
Your force has an X and a Y component.
Good. Noel says, hey, my force has an X and a Y component. Here, I'll even draw it. Here's my X component. Here's my Y component. Someone tell me, what's the only component of that force that's actually doing work on the suitcase?
The X component.
Good, X component, right? So I'd like everyone to please complete this problem. Sorry about my coughing. Complete this problem. Get me, how much work does he do? And remember, only the X component of force is responsible for the work. The Y component isn't responsible. He's not going up. He's going horizontally. Good luck.
Mr. Shana, why is it so bright in here?
Oh, someone turned on both lights. I think the earthquake turned it on. 'Cause our great event. Yeah, I think some student came in here and turned on all the lights to see. The problem is once it's really bright, you turn off one light and then it starts, it's really dim. see what I mean? Yeah, well, you'll get used to it.
During calculus.
Okay, do you have it? Here. Okay, let's take a look at this. Is everyone getting that the x component of the force is 100 newtons times the cosine of 30?
Yeah.
So my work is not just force times distance, it's actually 100 newtons times the cosine of 30 degrees times the 10 meters. And what'd you guys get for that?
800.
Great, 866 joules. Great. So we get to a third equation, the equation that they have in the book. What if I told you that I have an object that has a displacement in that direction, but the force is in that direction with an angle theta in between them? Then what would the formula for work be there? And let's say you went some distance d. So it's force times d times what? Yeah, cosine of the angle, right? And so that's the formula the book gives you. Because the book is trying to remind you, hey, you've got to get the force in the direction of displacement, or the displacement in the direction of force. So this is the formula you get to mindlessly plug into if you're so inclined. But I just want to always remind you, work is the force in the direction of the displacement multiplied by the displacement, or the distance. Okay, let me give you another scenario. Let's say someone is running towards me and I have to stop them. So they run towards me, they slam into me. I'm exerting a force that way, but he and I go in this direction. That is, I'm exerting the force that way, but we're going in the opposite direction. What kind of work do you suppose I'm doing now? How many people think in negative work? Hey, absolutely, I'm doing negative work. I'm exerting the force that way, but the motion is happening in the opposite direction. That's negative work. And you can see that easily by looking at this formula. What if this is the direction of my force, but this is the direction of my displacement? What's the angle between force and displacement now? Is everybody thinking it's a straight angle, 180 degrees? Cool. And what's the cosine of 180 degrees? Yeah, thank you very much. -1. Whoever said that. Okay, thank you very much. Easy enough. Yeah, -1. So you see, that's how you get your negative work. You've got a force acting in the opposite direction of the displacement. Let me show you an example of that right now. Remember this guy pushing on the box, pushing for 5 meters, and he's exerting 100 newtons. But suppose he was going at a constant velocity. So he's pushing the box at a constant velocity. What must be the net force on that box if he's going at a constant velocity? Yeah, 0. So he's exerting 100 newtons of force to the right. There must be 100 newton force acting to the left, because the net force has to be 0. So what do you suppose that force acting to the left would be? Yeah, how many people think in friction? Okay, good for you guys. So yeah, so we've got friction. We've got kinetic friction, which is equal to 100 newtons. So I've got kinetic friction of 100 newtons that way. I've got the box moving 5 meters that way. Tell me, what's the work that kinetic friction does? How much work does kinetic friction do? I'll give you a hint. It's 100 times 5, except... Oh, please, someone. How many? Okay, I'll give you 2 choices. It's either positive 500 or negative 500. How many people say that friction is doing positive 500 joules? How many people say negative 500 joules? Yay, okay, thank you very much. Yeah, negative 500 joules, right? Because the friction force is opposing the motion. And we're going to discover later that since the net work done on this box is 0, right? I got 500 positive joules being done by me and 500 negative, negative 500 joules being done by friction. The net work on this box is 0, so the box isn't going to go any faster. And we're going to learn about that on a later day, this idea that the network, you need to do net work on something in order to change its velocity. Well, hey, let me give you another scenario. Escalator. Here's an escalator. Escalator. Here's a guy here on the escalator. He goes up. Goes up 10 meters. This is a dude who weighs 800 newtons. I want you to figure out what the work done by the escalator is. The work done by the escalator. He's an 800 Newton guy. The escalator's taking him up 10 meters. How much work does the escalator do on him? I'll give you two choices. It either does 8,000 joules or more than 8,000 joules. You guys okay with that? Those are your two choices. The escalator either does 8,000 joules or more than 8,000 joules. Okay, you ready to vote? 800 Newton guy going up the escalator, 10 meters high. How many people say the escalator does exactly 8,000 joules of work on this guy? 0 of you. 1 of you maybe. Alfred, do you want to go with it? No? Okay. How many people say the escalator does more than 8,000 joules of work on it? Okay, great. Everybody else. All else. Someone explain to the class, why is it more than 8,000 joules? Yes, Fatima.
He's accelerating up.
Okay, well, he's not accelerating, he's going at a constant speed, let's pretend. Because we know escalators, they don't accelerate us, right? We go to constant speed. But he's going at a constant speed up, okay. What else?
So the force up has to be more than the force down.
Okay, but he's not accelerating. Go ahead.
You don't go up an escalator straight up or straight across, you got an angle. And so the angle can't be greater than 90 and it can't be less than 0, so it's got to be, the cosine of that angle is going to be between 0 and 1, making the number larger.
Okay, all right. Is anyone thinking in terms of just, hey, the escalator's exerting 800 newtons, but he's going farther than 10 meters? I mean, from here to here is more than 10 meters. Is anyone thinking in those terms? Okay. Those of you thinking that way, of course, that's wrong, right? Because what's the only distance I care about? The escalator's exerting 800 newtons force up on him. Remember, this guy has two forces on him. He's got his weight, which is 800 newtons, and then he's got the force that the escalator is exerting up on him, which is 800 newtons, right? So what's the only distance that matters? Do I care about that distance? No. No, I only care about the distance in the direction of the force. The force is straight up. I only care about the straight up distance. You guys okay
It
with
would have
that?
been the sine angle then, right?
What's that? Say again?
It would have been the sine angle then, because
No, it'd still
it's
be the
y
cosine.
direction. But you just said it was the y direction.
Well, yeah, it's the y, but his force is 800, and his I see. But this angle here,
Yeah.
okay.
Oh, you're doing the angle.
Yeah.
Yeah, if I do that angle.
Nope, that's still sine.
Yeah, that's still sine, okay. Well then, okay. But regardless, you don't have to do any of that sine stuff. There it is, it's 10 meters. You don't have to do any sine stuff. I already told you what the distance in the y direction is, it's 10 meters. Okay, was anyone here considering friction force? Static friction? Tell me, since he's moving, and I have to say again, I'm really referencing your experience with escalators, because your escalator better be going at a constant speed. If your escalator is accelerating or decelerating, what's going to happen to the people on the escalator? What's that? What's going to happen to people on an escalator if it's accelerating and decelerating? Yeah, they're going to tumble off. It's going to be a disaster, right? So your escalator has to go at a constant velocity. So which means the x component of velocity of the escalator is going to be constant as well, which means there's no acceleration in the x direction. So tell me, what's the static friction force between the guy's feet and the escalator? if it's not accelerating. Look at me, I'm not accelerating. What's the static friction force between my feet and the ground? 0, right? Yeah, 0. So I just want you to see the only component of force the escalator exerts on the person is upward to balance his weight. The escalator is not exerting any X component of force. There's no friction happening because he's moving at a constant speed. So there's no static friction force acting on his feet in the same way that there's no static friction force acting on my feet. And so, yeah, so do you know how, remember how everybody voted for this? What's the actual answer? Is it going to be 8,000 joules or more than 8,000 joules?
I think.
Let me have a vote. How many people say their idea has been changed and they want to say that the work done by the escalator is exactly 8,000 joules? Okay, thank you. How many people want to maintain their wrong idea that it's more than 8,000 joules? Good enough. That's great. Good. You're an American. Yeah. I hope you see that's the right answer. 8,000 joules. And let me ask you this question. So we got the work done by the escalator is 8,000 joules. What's the work being done by gravity? Remember, gravity is acting down while he goes up. How much work is being done by gravity? I'll give you two choices. It's either negative 8,000 joules or it's something else. Something else. Yeah, it's got to have a U. Something else. How many people say it's exactly negative 8,000 joules? How many people say it's something else? Oh my God. Someone explain to the class, why is it exactly negative 8,000 joules? Say again, Chris?
Gravity's going down, so that's where your work has to be going.
Yeah, gravity's going down, his displacement is up. I don't know, negative 8,000. You guys okay with that? All right, well then, hey, it's time now to talk about energy. It's time to talk about energy. The definition of energy. We'll wait for that camera. Okay, here we go. I'm not going to hunt for the definition of energy. I'm just going to tell you. Energy. You know something has energy if it has the capacity to do work. Energy. The capacity to do work. If something has the capacity to do work, then it has energy. Tell me, do I have energy?
Yeah.
Sure. Why? How do you know I have energy? Because I can do work. I could take little Poocha and lift her up. Exert a force over a distance. Great. Did work on it. Work. What you must do to an object to change its energy. Work. What must be done to an object to change its energy. I'm going to talk more about that in a moment. Two types of mechanical energy. There's two types of mechanical energy. The first type is kinetic. Kinetic energy. That is the energy of motion. Something has energy. Something has the capacity to do work by virtue of its motion. Suppose this is a 1 kilogram mass. Suppose I gave this 1 kilogram mass to Justin, who's an accomplished football quarterback, and I asked him to throw that mass at my stomach as hard as he can.
Ow.
Okay? So that this mass has now been propelled. This mass has a tremendous amount of kinetic energy. That is, it's going pretty fast, and it's going to hit my stomach. Does this mass, by virtue of its motion, have the capacity to do work? That is, when this mass hits my belly, will it do work on my belly? Absolutely, right? The mass is going to hit, it's going to, right? But meanwhile, that mass is exerting a force over a distance, right? So that mass is doing work on my belly. So I want you to see, when an object is in motion, it has the capacity to do work, just like this mass would do work on my belly. And we call that kinetic energy. Something in motion has a capacity to do work, and we call it having kinetic energy. The second type of mechanical energy is potential energy. And that's the energy, energy due to an object's position or state. Let me ask you this. This mass, I am holding it still. This mass is completely still. It has no kinetic energy. Does this mass still have the capacity to do work? What could I do for this mass to realize its capacity to do work? Yeah, drop it, let it go, correct? If I let it go, what's it going to do? It's going to fall. What's going to fall on?
Your toe?
My foot. When this mass falls on my foot, will it have the capacity to do work on my foot? Sure, it'll hit my foot and break some bones and exert a force over a distance, right? And do work on my foot. See? Here, I'm going to show you now. You ready? Here it comes. No, I didn't do it because I was afraid. Okay. That type of energy, by the way, is called gravitational potential energy. We'll learn about it later. This guy has the capacity to do work due to its position relative to the floor. Let me show you another type of energy, spring potential energy. See this mass? I'm going to put it on this spring, and I'm going to compress the spring. Does this mass, due to its position on this compressed spring, does this mass have the capacity to do work? Sure, I could point it at Gavin, right? And I go, boom.
Come on, Gavin.
But if it was heavy enough and the spring were stiff enough, you know, this thing could have shot out and hit him and did work on him, right? So this object, due to its position on this spring, has the capacity to do work. And we would call this spring potential energy or elastic potential energy. There's another type of spring, not one that just compresses, but how about springs that stretch? These are rubber bands, and they have the capacity to do work, or at least an object on a stretched rubber band. Here's my rubber band, and then I do this, okay. And then this is a 3x5 card that I bent so that I can make it a projectile. What if I were to shoot this at one of your eyeballs? Could it do work on your eyeball?
I got glass.
Sure, well, you got glasses, good. But see, that's why your parents say do not play with these sorts of things in the house. Because if you hit someone in the eyeball, it will do work on their eyeball and damage their eye. I would rather shoot at that homework hotline poster. So here we go, you ready?
Oh.
See, this is what I did the last two periods. I think I went at too oblique an angle. Here, I'm going to go right
Gavin,
on top.
elbow
of
down.
it. Here, or maybe I'll do the Halloween Town. Does anyone want the Halloween Town poster?
No.
Okay, here we go. Halloween Town.
Oh, okay.
Wow, it just bent it. Wow, that's a good poster. High quality poster. I've been smoking that homework. We're also going to learn later this semester. We're going to learn about electrical potential energy, where if I have two, let's say two positively charged objects near each other and let one of them go, this guy exerts a repelling force on this guy and he would have the capacity to do work. He'd shoot off and he could do work on something. So that's it. These are the two types of energy. And then one more thing I want to mention, okay? Consider this guy. Let's say I want to give him kinetic energy. What am I going to have to do to this guy in order for me to give him kinetic energy?
Put it in motion.
People are saying throw it or whatever, but I hope you see it, do work on it. Exert a force over a distance. If I exert a force over a distance on this eraser, it will acquire kinetic energy. I'm changing its energy from having no kinetic energy to having kinetic energy by doing work on it. Work It must be done to an object in order to change its energy. All right, hey, good luck on tonight's homework. And we're done. Thanks.